So we're going to wrap up chapter 2 with measures of position, kind of rounding out all the different ways that we can display and interpret data that's given. Again, all within this descriptive branch of statistics. We'll cover after this some basic probability, and then everything else just becomes much more advanced with analyzing information and trends that we won't have time to cover. But quartiles are something that are used a lot. They're a subset of fractiles. Fractiles are numbers that divide ordered data sets into equal parts. That ordered part is very important, from least to greatest. And so a lot of times you'll see them broken up by every 10% or 25% or 20%. Quartiles are the 25%. The data is ordered. Ordered data is evenly divided into 4 equal parts, okay? So you have the lower 25%, the second 25%, the third 25%, and then the upper 25%. And the boundaries are the first, second, and third quartile. So the first quartile is 1/4 of the data falls on or below that line. So we're grabbing the first quarter of our data, the first 25%, and that is our first quartile. Okay, that's the upper limit of our first quartile. The second quartile is half of our data falls on or below that line. That's our median, our midpoint. Okay? Median is our second quartile. Third quartile is 3/4 of the data falls on or below that line. Okay, so that grabs 3/4 of our data, and it breaks it up into 4 parts. So our first example, we're given the amount of fuel in gallons per year that automobile consumers waste due to traffic congestion in the 15 largest urban areas, where a population is over 3 million. They're listed. Find the first, second, third quartiles of the data set, and then what do we observe? Okay, so again, when we're looking at observations, it's what do the numbers tell us? Okay, we could probably make some assumptions, but we don't have to don't look too hard. So we have to order the data first. So we've got our 15 cities. We put them in order. And usually the easiest thing to do is find your median first. Find your midpoint. Okay? Cut your data in half. And so we find our second quartile, and that's going to be at 31. And so half our entries are to the left, and the other half of our entries are to the right. Because we have 15 cities, and it's an odd number, we've got one number for our quartile 2. And so then we have 7 cities on the left, and we have 7 cities on the right. Okay? So data entries to the left are quartile 2, data entries to the right. Then from there, we take each quartile and we want to cut it in half again. Okay? Since we have 7 data values, that middle number, that fourth value, will be our quartile 1. And then that fourth value from the median will be our quartile 3. We'll split that data set in half as well again. So we've got 4 data sets. So when we look at our quartiles, that's the first 25% of my data. That's the second 25% of my data. That's the third 25% of my data. And that's the fourth 25% of my data. So approximately 25% of my data is in each of those sections. Okay? It's not going to be exact because depending on if we have even or odd numbers, and if half of that is also even or odd, it's going to make a difference. Okay?
So sometimes you have to do 2 numbers?
If we have 2 middle numbers, how do we find that median?
The average?
We find the average, but then we will actually include each of those 2 numbers in the second and the first half and the second half.
Oh.
So if I had another 31 here, okay, my quarter 2 would still be 31, but then I would be looking at splitting these numbers. So I would have to group 4 and 4, and then find the average for quartile 1 there. And then I would have 4 and 4, and find the average for quartile 3 there. Does that make sense?
Yeah.
Split it, the data, and then we see what's left, and we just keep splitting it. All right? So what do we notice about gas wastage? What else? What does quartile 3 tell us? Not where most of them are.
Below. That's the maximum.
We're below. So most of the cities waste 35 or less. Okay, that's what the quartiles tell us. That amount or less. It's that upper limit. So 25% of cities waste 26 gallons or less. Half of cities waste 31 gallons or less. 75% of cities waste 35 gallons or less. Okay? All right, same idea with tuition costs and $1,000 for 25 liberal arts colleges are listed. We can use technology to find the first, second, third quartile. So if we wanted to do it by hand, we would have to list all these out in order, okay, in order to find these points. But we don't need to. We can use our calculator. And just like we found our mean and our standard deviation, we can go into stats and we can type in that entire data set into our list. So we should go ahead and do that. Type that whole data set into our list. Useful for sure. How many numbers should we have in our list? 25. So make sure that your last number is 25. So once we've got our list and we go back into stats, just like we did before with calculating our one variable statistics, okay, it's going to be the second half of that list that we weren't really looking at before. All right, we've got our mean, 51.2. Since we're dealing with a sample, we have a sample standard deviation of 10.2. And then if we scroll down, we get what's called our 5-point summary. Okay, 5-point summary. Minimum, Q1, median, Q3, and maximum. It's our 5-point summary. It breaks up our data set into those quartiles, Q1, Q2, Q3, as well as identifying our minimum and our maximum values. 5-point summary is really important in statistics. It's used a lot as a very quick gauge for not only measure of center, but for also spread and identification of outliers. It's a very, very quick tool that's used in a lot of statistical analysis as kind of a first glance at analyzing the data. Okay? Every time I take a giant data set and I'm doing a statistical analysis on it, I'm trying to identify trends or do regressions or whatever, I do a real quick 5-point summary with the data to kind of analyze and get an overall idea for what the spread is. And then I can go based off of that for any further analysis. So we've got our 5-point summary. So our first quartile, our Q1, is listed at 47. If we did it by hand, we would find that I would have to average those two, not those two, those two values. Okay, that's Q1. Q2, or my median, is at 55. And I think it's specifically third one. This one right here. Okay, that's our Q2, our median, and 58.5. That's our Q3. 58.5. And then also listed on our 5-point summary, which we'll be using a little bit more in depth, is our minimum value and our maximum value. Maximum and minimum. Okay? What trends do we notice? Yeah, the difference between our minimum and Q2 is a lot larger than Q2 and our maximum. Any other trends, patterns? Describe what's happening. These colleges cost less than $55,000 a year. And we actually have a formal way of identifying an outlier. We'll get to that a little bit. But by noticing, hey, there's this really big difference between our minimum value and our Q2 compared to our Q2 and our maximum, that's one of the ways that we can use this 5-point spread to kind of identify, do we have any outlier data? Do we have anything that's unusual? Okay. Well, next thing we're going to look at is, and it's part of this 5-point summary, is the interquartile range. Okay, so it's the measure variation for the middle portion of our data, the half. Okay, half of our data. So from Q1 to Q3, the range between those two values. Okay, so if I have a Q3 of 58.5. and I have a Q1 of 47, what is my interquartile range? 11.5. We want to find the difference between our Q3 and our Q1. Okay? That gives us our interquartile range. Now, using the interquartile range, we can identify, do we have any outliers? Okay? Any data entry that is 1.5 times the interquartile range above or below Q1 or Q3 is considered outlier data. Okay? So we want to take our interquartile range and we want to multiply it by 1.5. All right, well, if I take 1.5 and I multiply it by 11.5, what do I get? So then we want to compare to see if I have any data values, 17.25, above or below my Q1 or Q3. So I take Q3 and I say, okay, if I have 58.5 plus 17.25, what does that give me? 75.75? Yeah. Anything above that for this data set would be considered an outlier. Do I have any data values above 75.75? No, my maximum is 61, okay? So the right side is fine. Then if I take my Q1, 47, and I subtract 17.25, what do we get? Anything below that, so anything above or below these numbers are outliers. Do I have anything below 27.7 or 29.75? Yeah, our 19. 19 is going to be considered an outlier because it is below this limit. 19 is an outlier. Okay? 19 is an outlier because it is below that 1.5 interquartile range from the Q1. Now, using our 5-point summary, what we often do is we build what's called a box and whisker plot or a box plot. Okay? Box and whisker plots because it's called such because it's a box with some whiskers. Clever name, right? Okay. Also often just referred to as box plot. So it's again an exploratory analysis tool that highlights the important features. That 5-point summary. That 5-number summary. Minimum, maximum, Q1, Q3, and median. Okay? So the box is all the values between the Q1 and the Q3, our interquartile range. And then from the box, we draw whiskers out towards the minimum and the maximum. And the benefit of the box plot is it shows us the spread for each of those groupings. It gives us the spread overall, gives us the entire range of the data, and shows us how spread out the entire data range is. It also gives us our interquartile range, and tells us how spread out our middle 50% is. We have this vertical line that runs through the median, so it also breaks down the second 25% and the third 25% to show us how spread out each of those subsections are. And then because of the whiskers, it shows us how far away our minimum and our maximum entries are from that middle 55%. The longer the whisker is, the more likely that it's going to be an outlier. The shorter the whisker, the less likely it's going to be an outlier. Okay? So taking the same 5-point summary from before, we can draw our own box and whisker plot. We take a number line and we plot the points of the 5-point summary. We start with 19 and 47, 55, 58.5, and 61. Doesn't have to be perfect, but close is good enough. Sometimes close enough, it really is. It's close enough. Okay? So we plot our 5-point summary. We draw a box around our middle 50%, and we put a line through our median. So that shows a couple things. It shows the overall spread of our middle 50%. It also shows us that the second 25% is more variable or has more spread than the third 25%. So once we get above that median, those values are much closer together. Then we draw whiskers connecting Q1 to the minimum and a whisker connecting Q3 to the maximum. And now we can see visually with the box plot, holy cow, 19 is really far away. 19 is probably an outlier. And we proved that it is. The longer that whisker, the more likely we are to have an outlier. But even our maximum value is not very far away from our middle 55%. So that's definitely on that higher end. We can see that most tuitions are in the $50,000 to $60,000 range. There are some that are lower, but be prepared to pay somewhere around $50,000 to $60,000 a year for your college tuition at these liberal arts schools. Another type of fractile that shows up a lot is the percentile. It's another type of fractile. So usually it's quartiles and percentiles. Quartiles breaks it up into quarters. Percentiles breaks it up into percents. 100 pieces. Okay? An ogive, a cumulative frequency distribution, is generally, or can be often written as a percentile when we break it up. Percentiles are always going to be in that ogive because it is cumulative percent. Because we're looking at everything that is from that point and below. Okay? That point and below. So the ogive represents the cumulative frequency distribution for the SAT test scores of college-bound students in a recent year. When you get your SAT scores and you find your percentile, that's telling you that you scored better than that percentage of students. So if your percentile rank on your score is 90th percent, that means you've done better than 90% of the people that took that test during that specific time frame. Now, don't conflate percentile with score. It's just relative. 90 percentile doesn't mean you got 90% of the questions right. You just did better than 90% of the people. Okay? An average score, if you did perfectly average, okay, that would put you right at the 50th percent, right in the middle. Half the people did better than you, half the people did worse than you. That would put you at perfectly average. Okay? The better you do, the higher that goes. Now notice in the middle here, the rate of change is a lot more, and that's pretty standard if we follow that standard bell curve, okay, normal distribution. Most of our change will be in that middle area, and anything to the far end on the low end and anything on the far upper end, those are going to be extreme values. Those are either going to be really, really smart people or people that fell asleep during the test. which has happened. I once had a kid fall asleep during the ACT 3 times. Drooled all over his. That was really gross. All right, so when we're looking at percentile, we just want to figure out, okay, what test score represents the 90th percentile? We look at our 90th percentile and see where it matches up. And we go down here, and it's approximately, 1350. Okay? So approximately 1350. Okay? So 90% of students scored a 1350 or less. Or scored less than 1350. 90% of students scored less than 1350 on the SAT. When Bright Futures has scholarship requirements, SAT, okay, certain scores mark how much scholarship you get. They base those scores partially on percentiles. Because they go, we have a certain amount of money to give out. We can't give it out to 80% of the students. We can only give it out to maybe 20% of the students. We have enough money to fund 20% of graduates going to college. And so they set those scores to approximate and maximize, okay, how many students we can give it. Okay, here's what that cutoff is. And so they'll use that as a gauge, as I'm sure among other things, to try and determine where should they put that cutoff for those different scholarship levels based on the amount of money they have. If we want to find a specific percentile that corresponds to any specific data entry, we can use this formula where it's the number of data entries less than X divided by the total number of data entries. And then we multiply it by 100 to turn that into a percent. So with our previous example, with the tuition, we want to look at the percentile that corresponds to $57,000. Okay? So we're going to look at the number of data entries less than $57,000. How many data entries do we have that are less than $57,000? How many data entries do we have total? We have 25. So 15 divided by 25. Yep. And then multiply that by 100. 60%. Okay, so 57,000 is the 60th percentile. 60% of schools with these liberal arts majors are going to cost less than $57,000.
Why did we count this?
Because we're looking at the number of data entries less than. Because we're looking less than that percentile. So it's 60% are less than $57,000. Okay, last thing to wrap it up, the standard score. Okay, often used the Z-score. Represents the number of standard deviations a given value X falls from the mean. We talked about the empirical rule using our normally distributed data, and we could calculate the percent of data values that fall within 1, 2, or 3 standard deviations. Okay, 68% within 1 standard deviation, and we've got 95% within 2, 99.7 within 3. Okay, Z-score is that same kind of idea, but it allows us to get a much more specific value rather than just, it's around 1 or 2 standard deviations above or below. It gives us for a specific value exactly how far above or below the mean is relative to the standard deviations. And so generally, what we say is that usually we are within 2 standard deviations. Okay? 2 standard deviations, that's 95% of our data. So it's fair to say that if that range, if that's within 2 standard deviations, it's typical. It's to be expected. 95% of people fall within that category. But once we go past that, it's considered unusual. Okay? So we can have unusual scores between 2 and 3 standard deviations above and below. And if we go beyond 3 standard deviations, that's less than 0.3% of our data. That is very unusual. Okay? So 95% of our data will be here. 95%. Okay? And then 2.5 above, 2.5 above, and 2.5, I had that backwards, below. Okay? 2.5 above and 2.5 below will be more than 2 standard deviations. So that last 5% is considered unusual. The last 0.03% is considered very unusual. So we can use this formula to take our data value, we subtract the mean, and we divide by the standard deviation. And that tells us how many standard deviations above or below. And the usefulness of that is to tell us how unusual is that data point. Is it something that we could expect pretty often? Or is it something that is highly unlikely to occur repeatedly? So we've got 3 cars. We have the mean speed is 56 miles per hour and a standard deviation of 4. We have 3 cars traveling down this stretch. One's going 62 miles an hour, one's going 47 miles an hour, and one is going 56 miles per hour. Find the speed the z-score that corresponds to each one. Assume that we are approximately standard distribution. And then we can interpret to see which ones are likely and which ones are unlikely. So we take each value and we subtract the mean. Each value and subtract the mean. Each value, subtract the mean, and divide by our standard deviation. Okay? 62 minus 56. Divided by 4. 47 minus 56. Negative 9 divided by 4. 2.25. Okay. And then 56 minus 56. 0 divided by 4 is 0. So that's the z-score for each of those cars. 1.5, negative 2.25, and 0. So that's the number of standard deviations above or below the mean. So if I have a z-score of 1.5, does that put me above or below the mean? Above. 1.5 standard deviations. Is that usual? Yeah. So that is a usual speed. Okay? It's not unlikely to get that 1.15 or 1.5 standard deviations above the mean. Okay? Negative 2.25. Does that put us above or below the mean? Below. Is it a typical data value? No. Why not? It's unusual. Because it's less than 2 standard deviations. I'm sorry, it's more than 2 standard deviations below the mean. It's more than 2 standard deviations, putting it right around here within our unusual set of scores. Okay? So that is an unusually slow speed. Okay? Unusually slow. And then for our third car, what does 0 mean? It's usual. It is perfectly average. It's right there in the middle. It is 0 deviations above or below the mean. It is the mean. It is the mean speed. Okay? Which is typical, which is usual. Okay? All right. That wraps up our